Incredible as it may sound, an easy-to-spot problem in quantum mechanics, which supposedly has been noticed by the founders and which brings down the whole field of quantum mechanics. Pretending to be a scientific rather than simply practical engineering approach. Applicable in some limited cases for the lack of consistent scientific theory. Has been glossed over throughout the decades, giving it an only occasional attention. Quantum mechanics defines the position operator x hat as x, the momentum operator p hat as minus I h bar partial d dx. Let the ket vector psi sub x be an eigenfunction of the position operator x hat. Then, the eigenvalue-eigenvector equation quantum mechanics postulates for position in bracket notation will be as shown. Further, let the ket psi sub p be an eigenfunction of the momentum operator p hat. Then, the eigenvalue-eigenvector equation which quantum mechanics postulates for momentum in bracket notation will be as shown. Quantum mechanics presents the commutator of the position and momentum operator symbolically, as shown. Explicitly, the commutator of the two operators, according to quantum mechanics, is I times h bar. Further, quantum mechanics uses linear algebra to calculate the expectation value of that commutator. By applying axiomatically a rule, a prescription for that purpose. Only after this application, which is an organic part of the quantum mechanics machinery, comes the analysis as to whether or not this rule leads to sensible mathematical, let alone physical results. It may turn out, as it will, that the outcome makes no sense, but if so, and it really is so, it only shows deficiency in the methods of quantum mechanics, not in the desire of someone willing to apply these standard prescriptions. So, let's apply these standard prescriptions and try to determine the expectation value of the commutator, exactly the way quantum mechanics requires that to be done. For this reason, quantum mechanics instructs us to sandwich the operator between the Braun-Ket expression of the eigenvector. Let's do it first with the momentum eigenvector psi sub p. This legitimate application of the standard recipe, following the rules of quantum mechanics for finding expectation value, however, brings us suddenly to a dead end. A step is reached whereby the recipe brings us to an integral which is not the needed Lebesgue integral. The Lebesgue integral the standard quantum mechanical procedure is supposed to produce is undetermined here, let alone that the standard quantum mechanical procedure does not bring about the expected proper normalization of the eigenstate psi sub p, making it infinity instead of unity. As a result, the following obviously incorrect equality is reached. The same result is obtained when using the position eigenfunction for the purposes of determining the needed expectation value. The inclination of those who like to use quantum mechanics uncritically, as just an engineering tool, is to forbid carrying out the above operations because they lead to nonsense. Nonsense stemming from the very standard quantum mechanical procedures applied. The rationale is that any time inconsistencies are encountered such as the above, they should be resolved by suitably modifying, faking, the functions. However, those who need to know if quantum mechanics is a scientific theory observe that a legitimate attempt to determine expectation values of operators such as the above leads to failure. The functions provided by quantum mechanics are non-integrable. If quantum mechanics is defined through concepts like Hilbert's space and Lebesgue integrals, and this is contained in the axioms, as is claimed, then quantum mechanics fails at its first step, that is, when deriving position and momentum operators of a free particle. They both do not fall into Hilbert space and fail in Lebesgue integrals. Thus, it should be well understood that there is no way to get out of this mess and remain in the realm of science with the machinery of quantum mechanics and its postulates. The only way to pretend a solution is reached is by fudging the eigenfunction quantum mechanics really obtains, by filtering it through a delta function distribution. This empirical approach will not satisfy a scientist, but it obviously works as a temporary solution for the lack of a consistent theory for the solving of some practical problems. To quote, "Resolve the problem. It is suggested that we deal with the off-diagonal elements, while fully admitting that when working properly, in accordance with the rules of quantum mechanics for finding expectation values, that is, dealing with the diagonal elements, the problem persists, as shown. Thus, instead of properly finding the expectation value of the commutator, by sandwiching it between the bra and ket psi sub x, those who like to use quantum mechanics uncritically propose to exchange the ket psi sub x by another ket, namely ket psi sub y. This means that, to accommodate for physical reality, we impose ahead of time, off the top of our heads, the unphysical condition, which theory doesn't derive, that a single particle can be at the same time in two different coordinates of space. That is, we impose ahead of time, rather than have quantum mechanics derive it. Quantum mechanics derives otherwise, that the particle is, quote, smeared in space. And thus, fudging the above properly obtained result, we get the equation shown here. How this leads to a delta function, and what other ramifications may there be, must not be dwelled further into, if the goal is to deal with a scientific theory. Changing the non-physical outcome of a theory, and replacing it with something which the theory does not derive, namely, that a particle is not localized but is smeared in space, as is imposed in this studied case, is not a signature of a scientific theory and method. The most quantum mechanics can be used after such falsification is as a generator of empirical formulae, just as the empirical formulae engineers use in their practical work. Empirical formulae come from no theory at all, but can be useful tools in solving practical problems. The fact that quantum mechanics is not a scientific theory, but the most it can be used, is a generator of empirical formulae, must come across clearly when presented to students. This deficiency must not be kept hidden by describing quantum mechanics as some great achievement of the science of theoretical physics. From the above, it turns out that the problems are deeper than just the psi function not being able to describe fully the system, as the critics of quantum mechanics have thought. It turns out that the question is about the complete invalidity of said theory as scientific theory. Therefore, all the conclusions about quantum mechanics as being characterized by non-locality and entanglement, leading to quantum computing or quantum teleportation, are all non-physical. As seen, quantum mechanics is failing to derive even its most important eigenfunctions, that of position and momentum of a free particle. This means also that the question for the interpretations of quantum mechanics, Copenhagen or otherwise, is moot. Also, Because of the above, there cannot be any philosophical ramifications from quantum mechanics. Empirical formulae can only be of some limited practical significance without philosophical implications. The road to restore the scientific character of mechanics, including its quantum character, is to develop correct understanding of motion in the realm of the so-called classical mechanics. This is the subject of other presentations.